Hi, in the previous video I talked about the two most popular risk measures, and I gave you expressions which are not really easy to look at least. Now in this video I will give you simple expressions for the two risk measures I introduced in the last video. So, simple expressions for var and ES. That's the title of this video. Okay. Now suppose x is a continuous random variable. So I'm going to say that if x is an absolutely continuous random variable, then you have these simple expressions for var and ES. So the expression for var is simply the inverse of the CDF of x worked out at P. And the simple expression for ES is 1 over P times the integral from 0 to P right? So these are the two simple expressions where okay. Alright, so let me put this in a box. So these are two important formulas for this course at least. Okay. Now I'm going to do 3 examples on how to use these formulas. Right. The first example is the following. Suppose the loss x follows a normal distribution with mean mu and variance sigma squared. The question is to find expressions for var and ES. Right. Now the first thing you must notice is that the CDF of the normal variable is given by this. Right, this is the CDF of a normal variable with these parameters, where phi denotes the CDF of a standard normal. Now to find the inverse function of this at P, what you need to do is the following. You just simply say set the CDF equal to P and solve for x in terms of P, and that will give you the inverse function of the CDF of x at P. So this implies that Okay, and this implies that this implies that x is equal to mu plus sigma right. So what we have shown is that this is the inverse function of this at p. So hence the expression for var is this. This is the expression for var. So let me put this in a box. Now the next thing we need to find is the expected shortfall. So to find the expected shortfall, I will use the formula that I gave you in the previous slide, which is 1 over p times the integral from 0 to p of the var, which is okay. So subbing this into this, you can write like this, right? Now doing the integration, will give you the following. The first term will give you mu p, and the second term is the integral from 0 to p of sigma times okay, and this you can write as, if you divide by p, you get mu plus sigma. You can pull it outside the integral, so it's sigma over p times the integral of from 0 to p of phi inverse t at dt. So hence what we have shown is the following. We have shown that the expected shortfall of x at p is given by okay. So let me highlight this. Okay, so this is example 1. The next example I'm going to look at is the following. Example 2. I'm going to suppose that the loss x follows the uniform distribution on the interval from A to B. And we know that the CDF, from your previous courses, you will know that the CDF of x for a uniform distribution is this, right? All right. Now to find the var first, we need to set the CDF equal to P. So you're going to set this equal to P and then solve for x in terms of P, which means this. So this is what you get for x in terms of P. So hence var is equal to A plus P times B minus A. Okay, so this is the expression for var if the loss has the uniform distribution. Now to find the expression for expected shortfall, okay, so this becomes 1 over P times the integral from 0 to P of A plus T times B minus A. Okay. Now if you integrate this with respect to T, you will get this, and you take the limits at 0 and P. The limit at 0 is 0, so you get 1 over P okay, and hence we have shown that the expected shortfall for when the x follows the uniform distribution is equal to A plus P by 2 times B minus A. Right, this is example 2. Now the final example, example 3, I'm going to suppose that x follows the exponential distribution. So suppose x follows the exponential distribution with parameter lambda. And you should know that the CDF of an exponential random variable is given by this. Okay. So in order to find var, we need to set the CDF equal to P. Okay, which implies that is equal to P, which implies that this, and this implies that it's equal to this, and this implies that x this implies that the var, when x has the exponential distribution, is equal to minus 1 over lambda times log of 1 minus P. So let me highlight this. Right, and next thing is I'm going to find the expected shortfall. Right. So the expected shortfall, I'm going to use the same formula. Which is 1 over Okay. Now we worked out already what var is, so subbing that in, you get minus now the integration of log of 1 minus t is not difficult, but you will need to use, I mean, there are many ways you can do this. One way is to use something known as, excuse me for the ink, something known as the integration by parts, which you should have learned in your first year. So you should apply integration by parts. This is what you will get. All right. Let me get rid of the red ink. Excuse me for that. Okay. So I have used in this line here, I have used integration by parts. Okay. All right, now let's try to simplify. So you get minus 1 over lambda p. The limit at p is p times log of 1 minus p, and the limit at 0 is 0. And this you can write as follows. All right. Now you will see in a minute why I'm doing this. Okay. I'm going to group this like this, right? So this will be right. Now I'm going to divide this by this, this by this, so that will give you okay. Now the integral of 1 is t, and the integral of 1 divided by minus 1 divided by 1 minus t is plus log of 1 minus t. You take the limits from 0 to p. Right. So this gives you minus 1 over lambda p log of 1 minus p. The limit at 0 is 0, and the limit at p is this. All right, so hence we have shown that the expected shortfall when x is a exponential random variable is equal to this, right? Right. So that completes the 3 examples in this video, and in the next video I shall give you proofs. You may recall that in one of the previous videos I gave you the properties that must be satisfied by a coherent rest measure. There are 5 properties, right? So I shall give you proofs of those properties for var and es in the next video.